Welcome to Data Skeptic, a podcast exploring the methods, use cases, and consequences of recommender systems. Welcome to another installment of Data Skeptic Recommender Systems. In any recommender system, it's very common to have a high dimensionality problem. Let's consider e-commerce. Odds are you have hundreds, maybe thousands, could even be millions of items in the store. Similarly, you're going to have, if you're a site of any success, the same scales of buyers, or at least users. It's a very natural approach to apply some sort of dimensionality reduction technique to take that wide and often sparse data set down to something more useful and applicable with machine learning techniques. Principal components analysis, or PCA, is a well-established and popular technique. However, it's also a technique that can lead to unfairness, what it means for a recommender system to be unfair, and some other interesting concepts like power niche users are all covered in this interview. This highlights both some of the challenges of building recommender systems and some novel ideas for solving those challenges.
My name is David Liu. I'm an assistant research professor at Cornell University in the Center for Data Science for Enterprise and Society.
Before we get into sort of your career, can you talk a little bit about that center? Is there a mission statement or just an overall goal? What's going on there?
Yeah, the center is part of an initiative at Cornell to create more interdisciplinary connections within the university. So the bulk of the center is this assistant research professor position, which is post-PhD researchers who are usually collaborating across multiple schools within the university. So in my case, I'm primarily in computer science, but we're also working with folks in information science and the social sciences.
How do you end up developing those relationships?
Yeah, certainly a lot of those formed before I got to Cornell, with there being a lot of folks working on questions like the fairness of AI and the impacts of machine learning on society in general. But also some of it is organic, just being in Ithaca and everyone being concentrated in a close common space, physical space, is also helpful to create those organic connections as well.
And could you share some details on your specific research interests?
I finished my PhD this summer at Northeastern University. In my PhD, I was focusing primarily on questions related to fairness of machine learning and this intersection with network science and complex systems, which I know listeners might be already familiar with. But yeah, extending this question of not only how do computers and technology impact humans, but what is this intersection with the interactions among humans and computers? Since starting at Cornell this fall, my interests are perhaps honing more in on this area of recommender systems, but also just how can technology and machine learning models capture preferences? So obviously recommender systems do this, but just more broadly, how good are they at capturing our interests, which might be changing and fluid, but also more importantly, from a critical perspective, for maybe niche users or minority groups, marginalized groups, how do these models not capture our interests? And if they are not capturing our interests, what instead do they think about us?
So I assume there's no bad actor in here saying, if is minority true, then do a bad job. How does it arise that a minority group doesn't get the ideal outputs?
That's why this boils down to a technical question, because it's essentially unpacking maybe the hidden effects of modeling choices that we've made along the pipeline. I guess at the very high level, it boils down to maybe this intuition that a lot of people have, which is that if we have more data for one group, then perhaps because it's minimizing some sort of optimization problem, it will fit that group better because there's more data. Maybe some groups of users or people in general are easier to learn than others. And so I know that on this podcast, we've already talked about popularity bias, but there is this phenomenon where perhaps people who like mainstream content are somehow easier to capture. If I can figure out that you like Taylor Swift, for instance, maybe that already captures a big amount of your listening behavior. But for a more niche user, maybe you're into some complex area of some subgenre. Just knowing a single artist you like might not capture very much of your overall complex identity. So you might get this interaction effect where for some subgroups of users, we both have less data and they're inherently more complex to characterize. And so even without explicitly trying to harm these users, the mechanisms that we learn with might underperform for these groups.
Well, when you have a minority group, off the top of my head, the three ideas I have are collect more data, which if possible, great, but not always. Upweight them somehow in your process. And my third might be the same as my second, which would be apply some sort of regularization process to your loss function or whatever. Broadly speaking, is that the umbrella of ideas, or is there a lot more creativity out there for how to approach the problem?
Certainly. I will briefly backstep, which is I would say there's this first question of what are the groups in the first place? And that's where some of my research has been. And then I'll talk about, once we've defined groups, how we can handle them.
Sounds good.
The question of what are the groups is an interesting one, because certainly if you're answering a social question or a fairness question, you might start with something like demographic groups or use attribute labels that you might have, which is a good starting point. But then also in a lot of these applications, maybe we don't have that data, or maybe those aren't the right groups to analyze. So for example, in a recommender system, perhaps it's more natural to divide people based on whether they're mainstream or niche rather than based on a common demographic attribute, for instance. And so answering the question of what is the right group to analyze is a good starting point. Where my work has contributed is if we truly don't have a label, maybe we can infer groups. And so we take data, look at the underlying similarities between people, and you can view this as an extension of clustering. Group people based on similarity to infer groups based on behavior. I can say more about that later. But now going back to your original question, if we do have groups of people, indeed, I would say the strategies are either divided along the machine learning pipeline. We can either do some kind of pre-processing where we filter data, maybe just remove people who are outliers, like the people who have thousands of listens to a single artist, maybe remove those. We can then do in-processing, which is the more regularization, upweighting, kind of diving into the black box and tweaking something. Or we can do post-processing and maybe don't change the model at all, but after it's given us some scores or rankings, adjust those rankings and uplift certain ones and decrease others. Each of those approaches has pros and cons. Indeed, most of my work is focused on the in-processing part, which also has some interesting technical questions as well.
Well, I consider myself to be a bit of a niche listener, and I've noticed that sites like Spotify, they do figure out my niche pretty well. But if I have a complaint, it's that there's a very popular band in my niche that I do not like, that they can't seem to figure that part out, and it's constantly coming up in cycle. Makes sense, because it's generally people who like what I like would like that band. I just happen to not like them. So I guess I'm not one of your more like mainstream listeners. There are some listeners who'd be happy with just top 40. And as you said, they're easy to learn. Just put it on, and it'd be hard to not satisfy that user. I'm a lot pickier. Do you need a more specialized system for someone like me, or is there a continuum between me and a top 40 person?
Well, I guess how I've been approaching this question is, to what degree do we fully segment users from each other? And so this is more recent work that I'm working on, but you can imagine a continuum where on one side, we have the full extreme route, just fully segment users from each other. So maybe you only are interested in folk music. And so to give you recommendations, I will only compare you against other folk listeners and see what they like and generate some result. The other approach is, well, maybe other people have slightly different interests, but they have something to share to inform your interests. Or maybe you haven't even discovered everything out there that you like. And so the other approach is one single big model, train on all people, and then give outputs. And so currently I'm working on a project where we're aiming to have a single model, but intelligently pull in data from other people to give you the best recommendation possible. What you did mention, though, is an interesting phenomenon where when we look at minority groups, there might be users within the minority who closely resemble the majority. And so these individuals can often serve as bridges between the minority and the majority, which is an important role. And so understanding that bridging effect will be really critical to be able to capture the minority well.
When did you first get interested in recommender systems?
Yeah, that's a very interesting one. So for a long time, I was very not interested in recommender systems. There was something about them that just felt stale to me and perhaps just not very exciting. But this changed perhaps for two reasons. One was my realization of just how pervasive recommender systems are. I'll even start with the fact that in my conversations with friends and family outside of research, I often realize that folks maybe are not aware of just how pervasive recommender systems are in their daily lives. And the term itself might not even be that well known and might be even jargon. But this became more aware to me when I was interning at Meta as a research scientist intern. And I was working on their friendship recommendation system. And the size and scale of their friendship recommendation system was just far larger than anything I had ever seen before. To give a taste of that, in recommender systems, we have all these advanced techniques that we've developed, GNN-based techniques, and deep learning-based techniques. With a system as large as billions of users on Facebook, even the most initial simple quote unquote model can be too complex, computationally complex to train. But nonetheless, it showed to me just how large and present these systems are. So that was one area. But then a second area was these recommender systems captured the side of algorithmic fairness that I was interested in. Just to say a little bit about that, I view a lot of algorithmic fairness research as focusing on ensuring that models behave equally well for different groups of users. And how we define perform equally well is often that they give outputs that are similar for different people. And so regardless of a demographic attribute, this model should perform equally well. Where that was interesting to me and that captured a lot of my motivation for entering research, a direction I want to go deeper into is ensuring that not only do models perform well, but make sure that we can understand why they're performing either well or not well for a given group. And that involves going inside the model and looking at representations or embeddings, if we want to call them, and look at the literal vector of numbers the machine thinks that I am. And to analyze these embeddings well, recommender systems were, in a way, the ideal combination of my interests, where I can look inside the black box and leverage tools from network science and essentially matrix operations to understand what do these embeddings capture and what do they not capture.
Well, I'm sure it would be off the table for me to ask you for some trade secret about the friendship recommendation algorithm or whatever, but maybe a high-level question about your experience there. I believe you described it as a complex system. No surprise that, they would invest a lot of research and be optimizing, and that grows complexity. Is it a system so complex you only knew a part of it, or did you get a chance to grok the whole system while you were there?
It is certainly complex to the point where, as a single, albeit intern, it was certainly not possible for me to get a grasp of the entire end-to-end flow of this model. So to give a flavor of that, I mentioned just a little bit earlier this idea of embeddings and representations. And so the idea is that for a single person, I want to learn a vector, a series of numbers that capture this person well. And so you can imagine that Facebook, they have tons of data about people. And so one layer of abstraction is that maybe at the end of the day, we have a single vector. But to get to that single vector, other teams might focus on a particular area. So maybe it's your behavior on a given platform or your activity in a different area of the site. And so each of these teams might have their idea of what vector captures you well. And then you might have a meta model, a middle layer that combines these vectors to give you a final one. So on the team that I was on, we were more on the product facing side, giving the actual recommendation. So what we are often working with, I was working on is using that final vector, but to even understand how that final vector was generated is something I would argue that very few people have a full understanding of.
So the idea of describing every, let's say, user, it could also be a product, but describing objects, if you will, as vectors is useful for a lot of reasons I think my listeners will already know. Could we talk a little about the process? You'd mentioned sometimes it's embeddings. Another technique would be principal components analysis that I know you have some experience with. Is it fair to compare these? PCA as a dimensionality reduction technique could be used to make my data into a vector. Do you see it the same way?
100%. In fact, a large motivation to do this PCA work is that I view PCA, and you can also incorporate other fundamental factorization techniques like singular value decomposition, as the bedrock through which these more advanced matrix factorization or embedding models are based. And so to give a flavor of that, with PCA or singular value decomposition, we take our original matrix and we directly receive embeddings. We don't do any manipulations or smoothing, and we just, in a way, we can view this as a shallow model. So with PCA, even though Meta is maybe not using PCA to give their friendship recommendations, we can still view these more advanced techniques as built on top of, at the end of the day, a spectral analysis of some interaction matrix.
Well, in coming up with their friendship recommendation system at Meta, certainly they iterated, they tried lots of techniques, and they made decisions. They made choices about what complex thing they wanted to build. And you could say those decisions were biased or informed or whatever. When it comes to just PCA, it's a pretty non-controversial technique. It's just mathematics, really. There was no decision made like we're going to go left instead of right at any point. In what way could something like PCA lead to unfairness?
You're right that PCA is everywhere. We're talking about it here in the context of recommender systems, but more broadly, outside of recommender systems, it's commonly used for pre-processing, fundamentally taking high-dimensional data and reducing it down to fewer dimensions. What PCA is optimizing for is quite simple, which is I have an input matrix, could be users as rows, items as columns, and I know which user has interacted with which item or how many times a user has listened to a particular artist. And I'm taking that matrix and then I'm trying to learn the best approximation of it as possible. So by approximation, I mean a matrix that looks similar but is probably not exactly right. The reason that's not exactly the same matrix is because I'm forcing it to be low dimensional. And so this is perhaps repetitive for some listeners, but I think it's important to start there because if the main purpose of PCA is to approximate the initial matrix via compression, we can then ask a social question, which is, okay, maybe PCA gives me the matrix that best approximates the original one. But if the original matrix is very large, if millions of users, millions of items, maybe for a subgroup of my original matrix, the best overall one is not the one that performs best for my area or region of this matrix, if you will. And so you can view this as maybe you've found the best common denominator, but that best average doesn't work well for all subparts of the matrix. And so in this work, we asked that question, looked closer, and found indeed it's not doing what we thought it was. Maybe it's giving the best approximation, but the way it's doing that is violating some basic assumptions that we have when we build recommender systems. And indeed, by violating those assumptions, it's not representing subgroups well.
You're one of the authors of the paper When Collaborative Filtering is Not Collaborative. Can you expand on what you mean by that?
Yeah, certainly. So collaborative filtering is the bedrock of much of recommender systems. And it's such a common phrase that we sort of use it as an independent term. But if we really break it down, the reason it's called collaborative is because the model might know something about me as an individual. I've listened to maybe a sports podcast and other artists on Spotify. But in order to give me recommendations, it needs to pull behavior from other people to inform my future behavior. So concretely, the model in a way looks at what other similar people have listened to. And if there's an artist listened to by someone who's similar to me, but I haven't listened to that artist yet, that's probably a good candidate. So at the end of the day, it's, finding similarities among people in order to give good recommendations. The way that PCA does this is by focusing on how different items or artists, in the case of music, which is the main concrete example we use in the paper, by figuring out which artists are similar to each other. So I really like to use this idea of genres. Maybe we can group artists based on genre. We might not have those labels, but by looking at the listening history, we can see these groups of artists are commonly co-listened to, and these other artists are commonly co-listened to. So identifying those similarities is what we mean by collaborative. But the question is, does PCA actually do this and find the similarities among artists? And in short, we find this answer is not quite.
Is that a shortcoming of the technique or of the data?
Yeah, certainly it is primarily a data problem. And so this stems from the fact that certain artists are listened to way more than others, which is perhaps obvious. But then at a technical layer, what that does is if we feed this data, imbalanced data to PCA, again, the goal of PCA is to best approximate the data. And so if I give you data where most of the activity is concentrated in a small region of this matrix, then probably what is best is to just focus on that region where most of the data is and represent it well. And in almost intentionally disregard the vast majority of your data matrix where there's far less behavior or activity that is captured. And so it is indeed because the data is so concentrated in a small subregime that this focus on approximation also lends itself to focus on a particular region of the data.
So it makes sense to me then how it would hurt niche items where, it can learn that, I keep saying top 40, but just, mega popular stuff. It's going to focus on hip hop before it focuses on second wave ska, right? Just by the numbers. So those two-tone fans might not get as good of recommendations. Your paper also outlines a distinct second mechanism where PCA can be unfair, and that's amongst popular items. That seems counterintuitive. Could you expand on that?
Exactly, yeah. So that was perhaps the more unintuitive of our two findings. And there, the impact on popular artists is that the model might overfit to these artists and essentially memorize who's already listened to them. So from the artist perspective, the idea is to most find people who A, have not listened to that artist yet, but also will probably like that artist. The problem is if the model is so specialized on the top 40, then it will overcapture who has already listened and not listened. And it will view people who have not listened to that artist also as people who probably do not like that artist, and is not able to disentangle this fact that maybe I haven't listened to them, but I do like the artist. So we view this as over specialization, or you can call it memorization, and essentially locks those artists in to its existing user base and doesn't expand the pool of users who might like the artist even though they haven't discovered it yet.
How many systems does your business juggle? ERP, CRM, HR, accounting, plus countless spreadsheets. Most companies waste hours piecing together answers from multiple platforms just to answer a single question. Scalar unifies every business system into one source of truth. No more spreadsheets, no exports, no chasing people across tools. Scalar understands where all of your complex company data sits, structured and unstructured, and powers a natural language interface where you can ask questions in plain English and get instant, accurate answers. Scalar works with Snowflake, Databricks, and every other data provider you trust. No migration needed. Scalar understands what your data means, where it sits, and lets you access it 10x faster, saving you time and money. Go to scalar.com and get your free demo today. That's Scalar, SCAYLOR.com. Once again, SCAYLOR.com. Get a free demo of Scalar and finally unify your business data once and for all. Well, so far we've talked about it theoretically mostly, and let's call it a hypothesis. It's a very intuitive one, but it's got to play out in the real data. I believe you looked at, is it Last.fm's music data set?
Yeah, so this is perhaps an older data set, but nonetheless a benchmark data set that we can play with. And so it's music data that is the particular one that we use. There's multiple Last.fm data sets. The one we use is mostly listening behavior from the early 2000s. And so what we looked at with that data is for a given artist, how well does the model capture who listens and doesn't listen to that particular artist? And the whole idea of PCA and these other matrix factorization techniques is that with just a few latent components, I can recover the majority of the data. Again, by recovering the majority of the data, I have a good approximation or compression. What we found is that at the artist level, individual artists depend on specific principal components. So while the top 5 principal components are maybe in aggregate the most important ones, if I'm just the Spice Girls, which I'm not, but if I'm just the Spice Girls, the model might not have captured my listener base very well with just the top 5 components. In fact, in the data that we looked at, the Spice Girls rely on the trailing components, which are often the ones that are discarded when we do PCA, in order to capture who does and does not listen to the Spice Girls. And so this is a real concern for folks using PCA, because the idea is I've found my top components, which are the most important overall, and then great, I can just remove the vast majority of these less important trailing components. But the problem is that some parts of the matrix are exactly relying on those trailing components to capture their listening behavior. And so we found that for individual artists, it's not as clean of a picture where the top components necessarily recover all the data.
Sure, we want to use the top ones that have the most information content to them, but on the flip side of that, we're dropping the tail, which has a lot of useful information in it, even if maybe not as dense. Does that mean we have to throw out PCA, or do we just take that as a realization and use those dimensions in different ways, or how do we proceed?
PCA has been around for almost 100 years. It's so prevalent. We are not trying to reinvent the wheel, but our goal is to both concretely and precisely identify mechanisms with which PCA can fail, or to raise awareness, but then also propose something that is similar enough, sharing the simplicity and the benefits of PCA that we like, but also that addresses these limitations that we identify. So the solution that we propose ends up being a bit more in the weeds of convex optimization. But the high level takeaway is that we want PCA to still give us top components that capture the data overall, but not suffer from this downside of over specializing on top artists. And so we find a way to boost less popular artists just enough so that the principal components we do identify capture group information and not individual artist level information. So again, the gold standard is we want to identify genres, groups of artists, and not focus on any single one by itself.
Could you talk a little bit about that boosting process?
Yeah, it's very tricky because very quickly by boosting, you can incur many downsides. So, one potential downside is that you might harm performance. And so, maybe data for less popular artists is less reliable. Someone accidentally listened to a ska artist, perhaps. Maybe it's noisier. But also, by boosting the less popular content, you might be focusing less on the bulk of users. So certainly there's a bit of performance costs that you have to be careful of. But also from a fairness point of view, you could boost the unpopular artists so much that they become the new popular artists. And so in our work, we identify this parameter that we can tune and control as a knob to get the right level of boosting. To define what is the right level, we have several evaluation metrics to capture that. And so the way that we approach this is let's start from the very low layer of do the embeddings work, and then let's look at are the recommendations good. And so the right idea for our approach was to find the sweet spot where on one hand, we've reduced the amount of specialization happening at the embedding level, while also still preserving the output recommendation performance. And so it's by looking at multiple evaluation metrics that we're able to find the sweet spot of boosting.
Could you share a few details on those evaluation metrics? What do you consider important in that process?
Yeah, so when we look at PCA, we can think of it as, at the end of the day, finding this matrix that captures how similar any pair of artists is. One way of operationalizing this harmful mechanism of specialization that we uncover is when the similarity matrix that PCA yields has large diagonal entries. And what large diagonal entries mean is that for a particular artist, it is only similar to itself and not similar to any other artist. So Taylor Swift is one of one, not similar to even other highly popular pop artists, for example. And so the diagonal entries are our way of concretely operationalizing and quantifying the amount of specialization. So by controlling this upweighting, we can see as we upweight less popular artists, how are these diagonal entries performing? And the idea is to reduce them while not harming performance.
And you mentioned introducing a parameter that then could be tuned. If I were to be the operator of the system you design, what does that knob look like, and how do I decide to turn it which direction?
Yeah, so the way this parameter works is it controls where the focus is applied when we're doing approximation. So if we don't use this parameter at all, PCA says, I want to best approximate the input in aggregate. So maybe there's a million numbers in this matrix, and I care about each of these numbers equally, and I want to best represent them. And our parameter says that for particular columns of this matrix, if it is a column that has very little data, again, a less popular item, then I might want to care a little bit more about that column than I would have otherwise. And so our parameter is essentially scaling up values in less populated columns in order to induce the factorization to care more about that region. So again, you can go too far, you can boost these unpopular columns too far, and then the model is over focusing in this tail region. That's definitely not desirable. So we want to boost it just enough so that it is simultaneously capturing the head and the tail.
Is this harmful overspecialization phenomenon unique to PCA, or might we find it in other vectorization approaches?
Certainly, we've seen it in other vectorization approaches as well. So we do compare against these deep collaborative filtering based techniques. So a common one that often people look at is light GCN, which is, again, a message passing GNN based type of factorization. What we found is that the answer is yes and no. So there is this specialization that still exists. But what message passing techniques do provide is that by smoothing the data and combining data from not just my immediate listening activity, but also listening activity from other users, it is able to mitigate the specialization to a degree. But what we actually have to be careful about with GNNs is that we can go on the far other side of homogenizing people. And so whereas PCA might have a very over specialization for some artists and under specialization for others, GNN based techniques might mitigate that, but often can result in the far other side of the spectrum of starting to view all artists as similar to each other. So the jargon that we might use for that is over smoothing. And so certainly there is this, again, challenge of not over specializing, but not over homogenizing either. And so upweighting and regularization remain important considerations for recommender systems.
So when using your item-weighted PCA, the sort of, I guess, modification, if you will, that you and your collaborators came up with, how did it perform in comparison to, I guess, plain vanilla PCA on some standard data sets?
Yeah, so essentially the takeaway of our results was that this item-weighted PCA approach was able to still preserve performance while also resolving these unfairness mechanisms. However, I will go one step further, which is that in some cases, we actually saw by handling these unfairness mechanisms, we can increase performance. And this is pretty contrary to the bulk of work on popularity bias. The bulk of work on popularity bias frames performance in tension with mitigating bias. We want to somehow boost niche users without harming overall performance. And what our results show is that learning good embeddings is good for everyone. And so because we showed that bad embeddings harm both unpopular and popular artists, there's an incentive for all people involved, popular or not, to have good embeddings. And so in particular, we found that for example, the Last.fm dataset, by improving the quality of the embeddings, we're actually able to improve performance and find users who like a given artist that we haven't seen yet.
My intuition is that there's going to be a trade-off between performance and fairness, and I've got to make a choice about how I compromise on one to get to the other. But to your point, if you have a good embedding that can benefit everyone, that seems great intuitively. And I guess we can define that it's good in terms of your measures are both performance and fairness. Do you have maybe more of a core intuition about what is the process really capturing? Why are these embeddings more rich and able to benefit everyone, and it's not a trade-off?
Exactly. So perhaps the right analogy to think about this is for a given person, I can think of what is the pool of people that are my people, so to speak. What is the pool of people that is similar enough to me that I can learn from their behavior, but also not so different from me that they have behavior that is not relevant to me. And so it is along this spectrum of either widening the pool or shrinking the pool that I view the concern. And so we can think of vanilla PCA as having a very small pool. And so certain artists are only similar to themselves or to a small handful, and there isn't this rich sharing between artists. On the other hand, maybe GNN-based techniques can widen the pool too far and pulling in data from and mixing artists that are not even that similar to each other. So it's finding the right size of this pool that actually helps both people and improves performance. And maybe in a toy setting, the right pool of people is clear and it's a specific genre. But more generally, finding the right width, but not too far width of this pool is a tricky challenge.
Well, if I can increase performance and fairness at the same time, it's a win-win. If I'm someone in an industry role, I want to roll that out into my production system. So I have to ask questions about scalability and asymptotic performance and this kind of thing. Is there an efficiency trade-off in your approach?
Certainly. So in our work, our primary goal was to give an algorithm that addresses these fairness mechanisms, but also satisfies some constraints that PCA provides. And so those were the primary objective. It is true that the approach that we do give has a slower runtime than vanilla PCA would. So that is an area of future work that we hope to extend our paper. But outside of the PCA work, we also see that in these deep models, cheap techniques might actually improve performance. And to give a little bit of flavor of that, in fact, we are seeing with more modern models that even performance and efficiency could be hand in hand. So the overall dominant paradigm is that more data is better. But what if the more data is not relevant data? And so if we're able to filter out the relevant and non-relevant data, then we might have a model that performs faster because we've removed a bunch of irrelevant data, and better because we've focused on the data that actually matters.
I know a lot of industrial recommender systems are pretty closed-lipped, don't necessarily publish or say what they do, so how could you know? But do you have a sense that industry has this wisdom or has taken this knowledge to heart?
I think that industry is, again, I'm not in it right now, but I will say that from my individual perspective, there is a wide chasm that currently exists where recommender systems are overall at the behest of increasing user activity on platforms. And so the amount of bandwidth with which we can modify and adjust and tweak them is quite limited because there's these constraints on how it affects user activity and maybe computational cost. So I think that I might be biased, but I think that's why studying recommender systems from an academic point of view is particularly exciting, because we can more widely characterize the realm of possibilities. And certainly these large modern recommender systems, I think, also have room to improve. It's pretty often that we meet individuals in our daily lives who are dissatisfied with the recommendations that they receive. And so I think there's real potential here to perhaps develop an alternative approach that I hope to eventually scale to a much larger level.
Well, there are some great benchmark data sets out there. You've worked with a number of them. Do you, as an academic, have what you need, or is there something more you'd like to get out of a data set department?
Oh, certainly. We have often utilized data sets that are either quite old or perhaps, they're commonly used and they're good as a benchmark, but maybe not representative of real world deployment. And so collecting more data is certainly an important avenue. In particular, collecting data where we can see how recommender systems perform over time will be really important. And so certainly that's an area that I think has a lot of opportunity to grow. A lot of these changes to recommender systems might not have clear impacts until down the line. And so it's very possible that you can imagine a scenario where maybe in the short term, the recommendations are not exactly what the user is expecting, but in the long term results in greater discovery, greater engagement, and greater agency and control for the user. So yeah, getting these longitudinal data sets is definitely very needed and tricky.
Yeah, I hope that those who produce them or could would start doing more of that. Well, earlier on, we talked a little bit about segmenting users. I don't know if we gave them specific labels, or at least one was the niche user. I know you've done some more recent work in which you've perhaps coined the phrase power niche users. Could you define what that is and what challenges that creates?
Yeah, power niche is definitely a term that I am using a lot these days. But quite simply, it's the combination of looking at how active a particular user is and how mainstream or niche their interests are. And this term came from perhaps an unintuitive place, which is that I had this conception that if I'm a niche user, maybe I'm not using the platform very much. Maybe the platform doesn't capture my interests very well. So I dabble with the little bit of niche content that exists, but otherwise don't engage much with the platform. What we saw is that actually niche users are oftentimes the most active on these platforms. And so maybe a good example is I care a lot about Szechuan restaurants in my city. And so I'm not going to just go to the top two that everyone else goes to. I'm going to try all of them to figure out which one I like best. And so this particular interest in a certain area can result in greater activity, greater exploration, and maybe even greater expertise as well. But at least in this work that we did, our main objective was twofold. One, highlighting that these people and users do exist, and maybe that itself is unintuitive. But then we went one step further, which is to say, not only do these users exist, but they offer valuable data that we should focus on. So while in the PCA work, we, doing upweighting and tuning this knob, with the power niche users, we can more concretely say this particular group of users has valuable data that benefits everyone else, and let's focus on them and upweight those users in particular.
And could you just touch on the process of how you upweight them?
Yeah, so we do something quite simple, which is literally give the values for those users greater magnitude in the loss function. So the approach was quite simple. And the idea is if we do something very simple, is it able to address the issue? Certainly, there is already this upweighting based on popularity, and that's commonly used, maybe sometimes called inverse propensity weighting. Less popular data gets upweighted, and that's very similar to what we did in the PCA work. So the main contribution here is not so much using a fancy new technical tool, but increasing the richness with which we are upweighting by. So not just upweighting less popular content, but specifically less popular content consumed by active people. Now, I have some hypotheses here. These are not proven, but some conjectures I might have is that by considering activity level, we can also filter among the less popular content. Certainly, there's a lot of low popularity activity that is noise that we don't care about, that is maybe errors or a one-off thing. I was briefly interested in this niche item, but I don't have long-standing interest. And so by focusing on the high activity users, my hypothesis is that we're able to filter out the noisy, less popular activity from the hidden gems that we do actually want to care about.
Well, David, is there anywhere listeners can follow you online?
Certainly on Twitter and Blue Sky and my website are good places that I hope to share more with listeners.
Sounds good. We'll have links in the show notes for people to follow up. David, thank you so much for taking the time to come on and share your work.
Thank you so much. I appreciate the invitation, and thank you.